Welcome, calculus students. Here's transformations of functions 1-3, where we're going to first get to know some common functions and then see how we can affect some translations with these transformations and then stretching and shrinking. First, your common functions. I'm going to give you a few more details than the book is giving here. A constant function constantly gives out the same output. F of x equals some c equal to a constant. And for a constant function, the domain is all reals. You can put all real numbers in. I'm going to be using this symbol a lot. That stands for all reals. Do you see the A and the R in there? For its range, though, you only get like the constant out. Y can only equal the constant. Y equals C. So it's kind of like if everybody was sent to the same birthday and the birth month function, the same birth month. It'll still be a function. It's just kind of boring. It's constantly flat like that. And this has a slope of 0. The identity function, also known as y equals x. We're going to see why it's the identity function when we do inverse functions later on. But your most basic of lines with a slope equal to 1 and a y-intercept of 0. Its domain is all reals. You put anything in, and its range is all reals. Anything can come out. The absolute value function, y equals absolute value of x, has this sharp corner right here. Sharp corner at 0, 0. And this is typical of absolute value functions. They're sort of like a break in the line. It can also be defined in pieces. In pieces, you could define it this way. F of x equals the absolute value of x equals x, which is the identity function, when x is greater than or equal to 0. Or it equals the opposite of x when x is less than 0. The domain is all reals, but notice now we have a restriction on the range, because the output of an absolute value has to be positive, so the range is y greater than or equal to 0. Square root function doesn't grow as fast as an exponential function or anything like that. It has a restriction on the domain that we've talked about before. The radicand, that's an even radical, means that the x's have to be positive, greater than or equal to 0. As a result, too, we get y greater than or equal to 0. It's basically part of a sideways parabola, but we don't get the bottom half of the parabola because then it wouldn't be a function. So there's the square root function. Another thing of note here is that the tangent line is vertical at 0, 0. You got a vertical tangent line there. So you can't say there's one slope. It keeps changing slope. Starts off with an infinite slope and then starts leveling off. But there's no horizontal asymptote, though. It'll keep increasing and get to any value, anything y greater than or equal to 0. The squaring function, f of x equals x squared. It's a polynomial function. Our domain is back to all reals again. The range, just y greater than or equal to 0. So in many ways, this is like the absolute value function. But it's got a rounded corner here. It's not a sharp corner. Vertex at 0, 0. Finally, the cubing function, f(x) equals x cubed. The domain is all reals, and the range is all reals. You can put anything in. And noticing right here, at 0, 0, it has a tangent line with 0 slope. Zero slope. Okay? Kind of like same thing with y equals x squared. There's 0 slope. This is a triple root. You're actually passing through the x-axis, but you're not actually, but you're flattening out as you pass through. Okay, let's go back and call some of these even versus odd. Any of these even or odd? Is this even or odd? Sure, it's always even. Even. Because it'll also have symmetry over the y-axis, because of that constant horizontal flat nature of it. Here, even or odd? Well, it's x to the first. It's odd. It has symmetry about the origin. Even or odd here? Even. It has symmetry with respect to the y-axis. Even or odd? Neither. No No symmetry here. Even or odd? That's right, even. Symmetry about the y-axis. Even or odd in the cubing function? Well, the big hint is y equals x cubed. It is definitely odd. Symmetry with respect to the origin. If you rotate this 180 degrees, it'll be back on itself. Now we're going on horizontal vertical shifts. Now in this aspect, it's really important that you do some exploring with GeoGebra, and it can also help you on your assignments as well to see what these horizontal and vertical shifts are affected by. So call up a GeoGebra, and I've done one of these already, where I have all the common functions labeled A through F, just like in our diagrams. And what you can do now, so you can focus on one at a time, is just turn some of these other ones off. Turn some of the other common functions off. So let's just look at right now the absolute value of x graph to see what's going on with some of these. There you go. Now we just have absolute value of x. And what I want to do in here is let's look at f of x plus 3. Okay, and we can see here that when we do the absolute value of x plus 3, or g of x as f of c of x plus 3, it actually shifts it not 3 to the right, but 3 to the left. That's because it's actually compensating. You're not adding 3 onto the x's to get the same graph. X will think I have to put a negative 3 to get the vertex I had before. So see how you would put negative 3 in? You actually get the absolute value of 0, so that's why it's 0. Now contrast that with if we make another function, call it absolute value again, but now we're going to go c of x plus 3. And notice there, you don't get a shift right. You have a shift upwards of 3. Okay? Let's try a few more. First, let's get these down. Okay, let's try another example now. Here's the square root function, or one of our common functions, square root function. Now when we do g of x is the square root of x minus 3, let's see what happens. Which way is it going to slide it? To the right or to the left? Actually to the right. X minus h is going to slide h units to the right. But notice it's inside the square root notation, so it's affecting the x's. Notice here now when we do h of x is square root of x minus 2, this minus 2 is actually affecting the y's, not the x's. So we have an effect on the y, and it actually slides the whole thing down to. Okay? Okay, so those are horizontal and vertical shifts. Now let's see what happens when we reflect over axes. Using reflections. Here goes. Okay, here we are with square root of x again. And we're going to experiment around with what happens if we put a negative on the x inside the square root symbol. Well, this is going to affect the x coordinates then, because it's inside the functional notation. When we do it, it flips it over the y-axis. In contrast, when we do opposite of the square root of x, it's outside the square root notation. It's actually going to affect the y's then, and this flips it over the x-axis. So the opposite of f of x, flip it over the x-axis, and f of the opposite of x flips it over the y-axis. Now let's look at some non-rigid transformations. They're called non-rigid because they actually change the shape. All the things we've seen so far, the translating and sliding and flipping over axes, that maintains the same shape, but these actually distort them. And here's an illustration. Okay, here we're starting with the absolute value of x function. And we want to see what happens if instead of adding or subtracting, we start multiplying. So here in absolute value of 2x, we multiply the x by 2 inside the function. So this is going to affect the x's somehow. But again, you get exactly the opposite effect. It compensates. So instead of stretching by 2, it shrinks 2 in the x direction. Now let's see what happens when we do the 2 on the outside of the function. Well, this should affect the y's. And this actually does the same effect, and they actually overlap with each other. These two things are actually doing the same thing because of the nature of the absolute value function. How could we actually get this to shrink and actually bring the absolute value down? Let's take a look at that. Think about it for a while. Okay, have a couple of other variations on here. P of x equals the absolute value of x divided by 2. Now it's going to affect the y's, but notice how it actually does shrink it down. It actually shrinks the y values. It does what we expect because it's on the opposite side of the equation from the variable we're affecting. Notice here, though, when we do q of x equals the absolute value of x divided by 2, when you do it this way, it's going to affect the x's. But instead of shrinking, they compensate by stretching out. So actually, q of x ends up in the same direction. The x's have been stretched out by a factor of 2. So how do you keep this straight? Well, when you're on the same side of the equation with a variable right up against it, it does the opposite effect of what you'd expect. But when you're on the opposite side of the equation with the variable you're affecting, it does what you'd expect. So keep that in mind. And now we're going to do a summary. Okay, to review what we did with stretching and shrinking. The red function here is the absolute value of 2x. Notice the inside, it's inside the absolute value notation, the functional notation, so it's going to affect the x's. But instead of stretching, it's actually shrinking the x's. On this next example, we have in green here 2 absolute value of x, and it's outside the functional notation, so it's going to affect the y's, but it actually does stretch the y's up. So it's a vertical stretch. Compared to absolute value of x all divided by 2, this is also outside the functional notation, so it's affecting the y's, but this is shrinking by a factor of 2. And finally, absolute value of x over 2, this is going to affect the x's now, it's inside the functional notation, but it does the opposite thing we expect, it actually stretches it horizontally. Now let's review all these different characteristics. First, let's scan through these one at a time here. Hang on, pull up the shade. There you go. Pulling down the shade now. F of x minus h is actually going to affect the x's. So it's a shift h to the right. And x plus h affects the x's, but it's a shift h to the left. F of x plus k, this actually affects the y's because it's outside the functional notation. It actually moves the y's up 5. Shift up k, because it's y equals f of x plus k. The effect is on the opposite side of the equation from the y. That's why it sort of agrees. F of x minus k is a shift down of k. Now let's look at what happens with our reflections. If we do f of negative x, this is actually a flip over the y-axis, because the points will keep the same y's but different x's. So it's a flip over the y-axis. Whereas negative f of x, you keep the same x, but you do exactly the opposite y. That's a flip over the x-axis. Finally, stretching and shrinking. For m greater than 1, f of mx, this is affecting the x-coordinates, but since it's right next to the variable, it's going to do the opposite thing we expect, so it's actually a shrink by a factor of m horizontally. F of x over m is therefore a stretch horizontally by a factor of m. M times f of x, now we're affecting the y's because we're outside the functional notation. And that ends up being a stretch vertically by a factor of m. F of x divided by m is a shrink vertically by a factor of m. Okay, that's it. Flange out.